Um, Hello, dear auditor. Yes, my name is Rokhmanova. I'm representing Ustikov Institute for Radiophysics and Electronics and Karasin Hakim National University. And I'm going to present you the work about self-induced THz-waves transmissivity of waveguides with layered superconductors. My report has following structure. At first, I'll describe what are layered superconductors in general. Then we'll give main perspectives to study them and formulate the main problem this work deals with. Then you will see main equations that were used in this work, and then I will show you the results that was obtained for two geometries. So, layered superconductors are periodic structure in which thin superconducting layers about 0.2 nanometers are separated by the thicker insulator layers about 1.5 nanometers and are electrodynamically related to each other by means of intrinsic Josephson effect. There are natural and artificial examples of such structures. Such a layer structure supports propagation of specific electromagnetic waves, the so-called Josephson plasma waves. These waves belongs to terahertz frequency range, which is very important for various applications, but not easily accessible for modern electronic and optical devices. This causes technological perspectives for studies on layered superconductors. From the scientific point of view, the interest in layered superconductors is mainly related to the specific type of plasma that is formed inside. An essential property of this plasma is its strong anisotropy of its current carrying capability. The current along layer is of the same nature as in bulk superconductors, while current across layers is of Josephson nature. Usually, Josephson plasma waves are studied theoretically for infinite superconducting slabs, but to fit actual experiments, finite samples should be considered since their sizes are about or even less than the wavelengths of terahertz radiation. Otherwise, the experiment and theory will not be comparable. In this work, we study case of finite sample that is placed inside of waveguide for two geometries when layers are parallel to the waveguide axis and when it is perpendicular to it. Yeah. To describe field inside, the electromagnetic field inside of layered superconductor is determined by the distribution of the Gauge invariant interlayer phase difference phi of the order parameter between neighboring layers. And phi is defined by a solution of a set of coupled Sangardon equations. Considering spatial variation of a field changing of field along z-axis greater than thickness of superconductor S and thickness of insulator D, we can write this set in continuous limit as following. Here, lambda NBL, lambda C are London penetration depths across and along layers respectively. Omega J is the Josephson plasma frequency, and phi 0 is the magnetic flux quantum. These equations are nonlinear. The nonlinearity originates from the nonlinear relation between the Josephson interlayer current and the Gauge invariant interlayer phase difference of the order parameter phi. We studied case of weak nonlinearity when we can expand sine phi as phi minus phi cubed divided by 6. For frequencies that are close to Josephson plasma frequency, the linear terms nearly cancel each other, and the nonlinear term plays the most important role. So our even waves of small amplitudes can be considerably nonlinear, and our case of weak nonlinearity leads to strong nonlinear effects. In addition, nonlinearity provides effective decrease on Josephson plasma frequency, and thus a nonlinear wave can propagate even below Josephson plasma frequency. Now we are ready to describe the first geometry. Here, layers are parallel to the waveguide axis. D denotes thickness of the sample, L1 and L2 are lateral dimensions of the sample. We choose polarization in the following way. For simplicity, we assume that electromagnetic field is uniform in z direction and electric field is perpendicular to the layers. Otherwise, the problem could not be solved without transformation of polarization. Using boundary condition, one can match fields inside of their superconductor with fields in vacuum region and obtain relation for a transmitted and reflected amplitude. This figure shows dependence of transmittance on normalized amplitude on incident wave for positive frequency detunings where linear wave can propagate in the layer superconductor, and for negative frequency detunings where they can't propagate, and that's why the value of transmittance for small amplitudes are that small. As you can see, these dependencies are more or less alike after some amplitudes, so the idea of this figure is that in this particular geometry, for high enough amplitudes, then nonlinearity plays the most important role, regardless of frequency detuning. The left figure here shows transmittance versus incident wave amplitude for negative frequency detuning, and the figures on the right is corresponding phase trajectories and 3D plot of A and A prime dependencies on normalized x-axis. This dependence shows hysteretic behavior. Let's quickly consider it in detail. If you increase incident wave amplitude, you should move along red axis. At first, you will achieve maximum at the point 3, but then you should move further to the point 9, and further movement is possible only by jump to the point 11. But when you decrease amplitude, at first the transmittance increase, then further movement is possible only by jump to lower amplitude branch, and this behavior will continue further to the point 10 when the last jump to lower amplitude branch takes place. The new figure on the right shows spatial distribution of electric field for 3 points. Here, vertical lines denote edges of the sample. As you can see, for the point 10, the layer superconductor is almost transparent, and that's why interference pattern in the first vacuum region is blurry. But for the point 11 and 12, the reflected wave becomes bigger, and that's why interference pattern becomes more pronounced. Now let's discuss the second geometry. Here, polarization is chosen in this way, and layers are perpendicular to the waveguide axis. In the same way as before, one can obtain relation for transmitted amplitude for negative and positive frequency detuning, and these dependencies also have a hysteretic behavior, and in addition, for positive frequency detuning, this behavior exists only for frequencies that are smaller than some threshold frequency. So, to sum up, I can say that here we study transmission of nonlinear THz-waves through a layered superconductor, and it turns out that layered superconductor is sensitive to incident wave amplitude, and one can attain total transparency of layer superconductor by changing incident wave amplitude, and in addition, these dependencies show a hysteretic behavior that is also very interesting. Thank you.
Why did you classify the THz-waves as nonlinear?
What?
Why did you classify the THz-waves as nonlinear?
No, it's not classification. Here we studied case of nonlinear waves. It's like a harder task to study it for nonlinear waves, and it is more interesting because when you change amplitude, you can get such results. But before, I also studied for linear waves, and I have also one more presentation of this conference, and you will see results for linear waves. So.
Okay, what you don't concentrated on the dimension of the waveguides. What is the?
Yes, I can show it. I think it is mentioned here in smaller, you see the smaller parameters? Yes. So usually for this case, for example, it is 0.1 centimeters, and these parameters is also like real parameters. It's theoretical works, but a thickness of the sample and other parameters are taken to make it real.
For understanding, what does it mean, Josephson plasma?
Oh. It is interesting case just because of this Josephson plasma. It's what I tried to say in this slide, that we have this different anisotropy if we have superconducting layer, and the electric we have different current in different directions. So it's like such a strange maybe that in one direction it is like superconductor, just ordinary superconductor, but in another direction it's not superconductor, it's just like set of Josephson, these connections.
Okay, I understand that, but what is the plasma? Plasma is some positive particles and negative particles, and together it's no charge. What plasma here and what does it mean, Josephson plasma?
Josephson because of the Josephson connections, because of the Josephson current.
So electrons have some specific behavior? Or
they tendulate through this dielectric, that's why Josephson plasma, because the Josephson connections.
The Josephson connection is clear, but
yeah.
Where is plasma here?
But everybody calls it plasma. So maybe I'm like not the best person.
Maybe it's for analogy that if you have some plasma, then there is some critical frequency and plasma frequency.
Yes.
And some waves with higher frequency can
yes, can propagate, but if smaller, then can.
But in that case, it's unreal plasma. But here,
it's a bit unreal plasma, yes.
Okay. Okay.
I'll try to improve myself.
Could you show please the slide for second geometry of?
Yep.
This is the question.
Yeah, I understand. Mm-hmm.
Please, could you please comment the polarization, because is it general case when all of three components of E wave are not zero?
Yes, of course, it's even more usual case, because usually you should have this coupling between layers, but in that case that I was talking before, we neglect this coupling, because otherwise we need to add this transformation of polarization, and it is usual wave you study this, yeah, that's...
Your wave is directed in Z direction, and
but it is polarization of wave.
Yeah, but how can you have is that not equal to zero? It's yes. Is it
is
transfer? Yeah.
You have only
the
two polarization.
You mean no? But if you have three, you have your coordinate system, and your wave is has all of the components.
Well, if you okay.
Okay,
Only this is the plasma thing. Because in the plasma, the wave is not transverse. There is a longitudinal component.
Mm-hmm.
That's the reason why there is EZ here.
Okay, it's time for questions.
Over.
Yes,
Thank you.